Right, we're going to have a look at the final section then. So what is the point is a question you might ask. Hopefully you can sort of just take it on good faith for now that we're learning lots of really useful skills and they're going to help us solve situations. But more generally, straight line equations are linear equations and lots of things are linear in nature. For example, you know, how much of something you might sell and how much you might take home. That could be like direct proportion. Converting between things is not quite direct proportion because there's sort of like a y-intercept, but it is a linear relationship. Sequences, temperatures and altitude, and you know, hundreds and probably thousands or tens of thousands of other things I would have thought. One thing we can do is we can start trying to model some of this, even though we haven't learned the most sophisticated maths in the world, we can still have a good go at this. So A-level maths mark, GCSE maths mark, some data from a scatter diagram. Your calculator is very, very good at turning something like this into a straight line graph, in fact. So it's going to try and find a y equals mx plus c that describes this situation that we're seeing. The idea is that once you then find that equation, you could use that to predict. So for example, you could take somebody with a new GCSE grade and say, roughly, we think they're going to get this grade. And in fact, this is actually sort of how performance management targets work behind the scenes. So a linear model might be suitable. It looks like a linear model might suit this one. Later on in the course, though, you might use other models as well. So you might use something like a quadratic, but for now, a line of best fit seems okay. Okay, so let's have a go at a question. We're going to do this one without the calculator, but your stats teacher will be able to show you later that you can input each coordinate and it will actually find these numbers for you. Okay, so determine M and C for the following. So we're allowed to assume that this goes through 0, 70 and 250, 20. So M, how do we find M? Difference in Y. I'm going to do right minus left, so 20 minus 70. 250 minus 0, so I get minus 50, minus 50 over 250. I get minus a fifth, which seems to sort of work with what I've got in front of me. Minus a fifth. It is hard to tell how shallow or steep things are with big numbers, but that sounds okay. What's the y-intercept? Well, they actually told me that by saying 0, 70. So we have minus a fifth and we have 70. Okay, interpret means you need to put this in context. So what does it actually mean? Don't tell me like abstract maths things. Tell me how this relates to the real world situation. So why don't we start with C? Might be a bit easier. So C means the altitude is 0. So when the altitude is 0, what the temperature is. So if we're sort of like climbing a mountain or something, I suppose it's telling you the initial temperature before you increase altitude, or it's telling you the temperature at sea level, something like that. M, what does M tell you? Well, M is like a rate. So the definition of gradient is what happens as you increase the independent variable, which is x, by 1. So if you increase the altitude by 1 meter, what happens to the temperature? That's what gradient tells you. So I would write that down exactly as we just said there. So C is the temperature at sea level, and M is how the temperature changes per 1 meter increase in altitude. And it does have to be per meter or for each meter, something along those lines. Okay, the temperature at sea level for each extra meter needs to be as precise as that, because that shows that you really understand what, for example, gradient is. That's sort of what that's assessing. Predict what altitude the temperature reaches 0. So we could extrapolate. How are we going to do this? Well, we're going to use the straight line that is kind of in the background here. So y equals mx, it was actually y equals minus a fifth x plus 70. So temperature is a bit like the y in this question. So if I make the temperature 0, 0 is minus a fifth x plus 70. I'm going to times both sides by 5. So 0 is minus x plus 350. So x is equal to 350. So that's my prediction. How reliable is this prediction? Not very reliable would be the answer, because I'm predicting outside of all of this data that I've got. This is called extrapolation, and it's notoriously dodgy in the world of statistics. So you have to be aware of that. And that sometimes is an exam question in its own right. So we're kind of making assumptions when we do stuff like this, and that's fine as long as you are aware of what those assumptions are. So for the previous question, we assumed that the change in temperature per each unit of altitude continues in the same way. So it's a fair assumption maybe, but it was a big assumption. We also assumed that this was a constant relationship because the gradient was constant, because it's a smooth, straight, steady line. Okay, and that's not necessarily the case. The current population of this place is 26,000. The year in 2017, the population increased by 150. We're going to look at population as sort of like the y based on the t, which is the x. So, you know, as you change the years, what happens to the population is the idea. Okay. And it says the population is m. So what's m here? M looks like it's a gradient, so we don't know. Times t, which is the years after 2017. So for example, you're going to say like 2018, you would write as 1. You don't put 2018 there, it says the years after. Okay. C, what would C be? Well, C is like the initial, because at the start, T will be 0, so you'll only have this, so it would be 26,000. So we could make the model like this. So the gradient is 150, because for each 1 year, the population goes up by 150. So we could write this here. This is essentially the model that he's using. What's the problem with this? Well, does population increase in a smooth, straight line? Not normally. Whether it's people or it's bacteria or something like that, we typically talk about exponential growth. If you look at sort of the world population over the past, I don't know, few hundred thousand years, it's very much like this. It's not like a smooth, steady relationship. And the reason is kind of obvious, that you have more people, then those people have more people as well. So it kind of balloons out of control. Exponential growth, you might call that. I'm sure you heard that word recently. And that's one of the later chapters. So population is not normally associated with a linear model. It doesn't work that well most of the time. Okay, you're going to see this coming up a lot later. That takes you to 5H. Okay, so modeling with straight lines for the end of the chapter.